And here very roughly I have shown the colours that you get as the temperature increases. At about 480 degrees something will glow faint red. At 580 degrees Celsius it's going to be dark red. At 730 it becomes bright red. At 930 bright orange. At 1100 yellowy orange. And at 1300 degrees Celsius yellowy white. In other words, as the temperature increases, so this graph moves this way and you get into the visible light region. This also accords with our own everyday experience. For example, radio waves, like television waves, are going through us all the time. But no effect, we don't notice them. Whereas infrared radiation, like something coming out initially from a fire before you can see it, you can feel it. You feel warm, there's some energy there. Visible light, you can see. Ultraviolet, if you stay in it long enough, will burn you. A lot more energy. X-rays will go right through you. And if you're exposed to too many, that can be very dangerous. What is happening here? All these electromagnetic radiation are simply increasing in frequency as we go that way, which means that that's increase in frequency. This way they're increasing in wavelength. But we've noticed that as you go in this direction, they also increase in energy. So the higher the frequency, the higher the energy. And so we can see why, if we plot the intensity against wavelength, we now understand why, as the wavelength shortens, that is, the frequency increases, the intensity increases. That much we can now understand. But our question is, why is it that it turns round and does that, when what we would expect is that it would just carry on like that? In other words, what we theoretically expect is this line here, which means that as you get to shorter and shorter wavelengths, higher and higher frequency, the intensity just keeps growing. And since this was kind of the visible light region, then here in the ultraviolet region, or here in the X-ray region, the intensity ought to be even greater. Now, let's just say that thank goodness it isn't, because if it were, when you sat in front of an electric fire, not only would you get the heat here, not only would you get the light here, but you would be absolutely frazzled by the ultraviolet and X-ray radiation. And that is called the ultraviolet catastrophe. Because if it happened, and it doesn't, but if it did, it would be a genuine catastrophe. So it's just as well that it doesn't. But why doesn't it? Why does the curve go up as we expect, but then start coming down again? That was the problem that Planck and Einstein turned their attention to round about the years 1900 to 1905. And they postulated that the energy that is in the electromagnetic waves has to be in packets of energy, which they called photons. And their argument was the photons cannot have more energy than is available. Now, how much energy is available? Well, we worked that out before. We showed that the energy is Planck's constant times T for any given atom. And therefore the argument is that you can't give a photon more energy than the average of kT. Or what we now know quantum mechanically is, if you've got an electron in an orbit around the nucleus, here's the electron, here's the nucleus, you can give it energy to drive it out to a higher energy orbit, but that energy cannot be greater than kT, because kT is the average energy that you've got in that gas. And consequently, when the electron falls back down again and releases a photon, that photon can only have the energy that was originally absorbed which is going to be an average of kT. Now, of course, as I said before, there's going to be a distribution of energies, the average of which is kT. But you can have energy higher and you can have energy lower. But the point is, the probability of getting a photon of much higher energy is very much less. And that's the reason why this curve does this. It increases with energy until it gets to a point like this. And this is where the energy of kT starts to go over this hump here. And now we're getting into this area where the probability of finding photons with this energy is very low. And consequently, this falls off. So yes, when your electric fire comes on, it's very possible that you will find a photon in the ultraviolet range or in the X-ray range. But the probability of them being there is in this region. Very low probability. So there's just the odd photon in the X-ray or the ultraviolet range. And that's why you don't get frazzled when you sit in front of the electric fire, because the amount of energy available on average is kT. That gives rise to a distribution that looks like this in terms of the probability of finding photons with different energies. And by the time you get up to an energy which would equate to the ultraviolet or X-ray range, you're down at this very low probability. And that's why the curve comes down quite sharply, so that you get hardly any ultraviolet or any X-rays. And the reason for that is that the energy has to be in packets, and the photon contains those packets of energy, and the energy can't be greater than the available energy in the gas itself, which per atom is about kT. For those of you who want the precise term, this was developed by Max Planck in a formula which is known as Planck's law, which says that B, which is spectral radiance, it's kind of another term for intensity, is 2 times h, which is Planck's constant, times nu, which is the frequency cubed, divided by c squared, the speed of light squared, divided by 1 over e, that's the exponential, to the h nu over kT minus 1. And this is the famous Boltzmann term. You've got the energy of the photon, which is given by h times nu. I've described that in some of my earlier videos, divided by the available energy, which is on average kT. And that dictates how the intensity will vary. And that's what generates this curve. So that's the Planck formulation. But I hope even if you don't follow that, you'll have understood why, thankfully, we do not have an ultraviolet catastrophe.